welcome to CEC lectures. Myself Dr. Preeti Chagwani from Department of Computer Science, Aryabhat College, University of Delhi. In this present series of operating system, we are going through the topic of memory management, and we have covered some of the lectures, and what topic we have gone through in memory management is all about the basics and the necessity of the memory management, and why it is done, or basically how it is done. Now in the upcoming couple of lectures, we are going to talk about various memory management schemes. Now, why do we need these various memory management scheme, and what all these memory management scheme are about? That's what we are going to cover here. So let us begin our today's lecture formally. This is about the memory management schemes, and it is the part of the topic of memory management. Now we all understand that memory, when we talk about, that means we are talking about, generally we are talking about primary memory, random access memory, and we all are aware that anything which is not available in memory cannot be accessed by our processor. So every data or anything, your programs or something like that, if the processor wants to access, that has to be residing inside the memory. Now memory, how it is arranged? This memory is actually in the form of array of bytes, and these array the cells of these arrays are numbers. So basically some array of bytes, or array of words, we can say. This is how your actual memory is there in this form. But when we talk about how a user perceive the view of a memory, that is altogether very different from what actual physical memory is. So what I am trying to say is, let's say for example, as a user of any programming language, let's say you have your various components of a program, various elements of the program. For example, you have variables, you have within that you have global variables, you have local variables, then you have your main program, then you have your subroutines, some procedures are there, some libraries are there. So this is what is actually the user view of memory, that user suppose or user understand all these components as differently stored inside the memory. But what actually physical memory is, it is the arrays, an array of various bytes, we can say, or various words, we can say. Now if we say to a programmer that in order to deal with memory, it will be he or she will be dealing the memory in terms of its physical properties, that is going to be very inconvenient for the programmer, very cryptic for the programmer, obviously, and also it is going to be inconvenient for the operating system. Now how operating system is here, because that's basically a bridge, or that's basically a platform between your hardware and the programmer. So what are we going to do here? We have a different view of the memory, and the user perceives it in a different view, or in a different lookout. So let's try to employ some kind of hardware that could provide a memory mechanism that mapped the programmer's view to the actual physical memory. That means we should have some kind of mapping arrangement, some kind of bridging in between, some kind of conversion in between, that is going to convert the programmer's view, or that is going to map the programmer's view to the actual physical memory. Now what are we going to gain out of it? Actually this kind of mechanism, this kind of mapping is going to be advantageous for both, that is for the system as well as for the programmer. Now system is kind of, we can say, is having more freedom to manage the memory according to its own, taking care of its physical properties and so on and so forth. While if we talk about programmer will be having some natural programming environment, what he or she perceives about the memory, that view is going to stand with him or her. So kind of more free programming, or more programmer can concentrate more on the logic of the program rather than being worried about the physicalities of the memory and the storage. So this is going to be a win-win situation for the system as well as for the programmer if we are going to employ some kind of mechanism which will kind of map the programmer's view to the actual physical memory. Now, what kind of this hardware mechanism, or what kind of hardware we are going to provide, which is going to have this kind of mechanism. First of all, this mechanism is known as segmentation, and this process of segmentation is done with the help of a special kind of hardware. I will be coming to the hardware details in a short while, but let us try to understand what actually this segmentation is. So, basically in short, if we talk about the segmentation as an entity, the segmentation is a technique of memory management, or we can say it is an approach to memory management. Now, what are we trying to say? Let us try to understand how this segmentation is being performed. So, let us take the view of a programmer first. While writing a program, a programmer thinks that main memory, it is a set of methods, or it is divided, in some chunks or some portions. One portion is having some set of methods, another one is having some procedures and functions, and it also includes some data structures, obviously will be there, like some arrays, or some linked lists, some variables, some stacks, and so on and so forth. So all these chunks are stored separately inside the memory. This is what a programmer thinks about a main memory. While we talk about segmentation, memory management scheme that is going to support this particular view of programmer about the memory. So what is happening here is this view of memory, we can say it's having it is named as a logical address space, and it is going to be a collection of segments. Now, what is segment? Segment, you can say it's an area, it's a chunk with a name and a length, obviously inside the memory. The address of a particular segment is going to specify both the segment name and the offset within the segment. So, we are going to have a segment in which we are going to store a particular element of the program. Let's say, for example, we say procedures, or let's say we say some functions or some variables. Those variables, those functions will be stored there, and that segment is going to have an address. That address is having two parts. One part is the segment name itself, and another one is the offset within the segment. So, offset is a kind of shift. I will be showing this with the help of an example. Now, programmer is going to specify each address by two quantities, as I told you. One is the segment name and another one is the offset. But for the simplicity of implementation, as we all are aware that in order to implement, numbers can be implemented, or numbers are easier to implement as compared to the names, which are nothing but strings. So, for the simplicity of implementation, we don't name the segments. We say that segments are numbered, and this is going to be closely related to what actually physical memory is. And this number is often referred by a segment number, and each and every segment will be we can say recognized with its segment number rather than by a segment name. So, basically a logical address space consists of some segments, and each segment is having its own address, which is having which can be shown in the form of a two item tuple. One is the segment number and another one is the offset. So, we are going to concentrate on these two things. One is the segment number and another one is the offset. Now, why we are calling it as a logical address? Because this is not the actual physical address which a memory is kind of having. No, this is what the view of the programmer, and that programmer's view will be somehow mapped into the real physical addresses. So, here this is what we call the logical address, not the physical address. Now, how are we going to do this? Obviously, this is going to be done with the help of a special kind of hardware, because your physical memory, as I told you, it's a one-dimensional sequence of bytes. and the programmer can refer to objects in the program by a two-dimensional addresses. So, it is going to be different. Here we have 1D array of a sequence of bytes, and for the physical memory, and for the logical addresses we have a 2-item tuple, one is segment number and another one is offset. So, we must define an implementation which is going to map this two-dimensional side of logical address into the one-dimensional space of physical addresses. So, this is what we need, and kind of we can say a bridging or a mediator in between these two views, or we can call more technically it can be called as a mapping. So, the mapping is effectively done with the help of a segment table. Now, what is this segment table? I hope you have heard about the file allocation table, which is more commonly known as FAT, something of that sort we can say. So, we have a segment table. Each entry in the segment table is consisting of we can say two parts. One is the segment base and another one is the segment limit. So, segment base and segment limit. Segment base contains the starting physical address. So, for example, there is a segment of let us say functions whose segment base is let us say 1000. So, that means these functions will be actually in physical memory, these functions are stored inside the address which is starting from 1000. So, the segment base contains the starting physical address where that segment is residing inside the physical memory, and the segment limit specifies the length of the segment. So, for example, 1000 is the base and 500 is the limit. So, that means that particular segment will start from 1000 in the actual physical memory, and it's it will span up to 1500 because the length of the segment is 500, and this length of the segment is specified by the segment limit. So, basically your segment table is having we can say it is a kind of array, or it is a kind of array of some tuples. Each tuple is having two items. One is the segment base or simply segment we can say, and another one is the segment limit. Now, let us look at the kind of whole this process, how it is happening inside the memory with the help of this segmentation hardware. So, as you can see on the screen, we have CPU is kind of generating some there is a column which is being generated, or there is, and we can say address which is being generated by CPU, which is consisting of two entries. One is S and D, and that is what your logical address is. Now, S is actually your S and D, both of these entries are concerned with the segment table which is being we can say accessed after generation of this logical address, and here we have S. S is your the segment number and D is the offset, or similarly we can say we have a limit and the base. So, in the segment table we have entries about S, also we have entries about D, and also after kind of we can say generating an address, complete address, we will be before generating a complete address we will be looking that whether the limit is less than the permittable limits. If yes, then only it's okay, then only kind of we can say a physical address is generated. If limit is going or we can say the length is going beyond the limit. So, for example, I am having 10,000 as the base and another 5,000 as the limit. So, what is happening, the total span of that particular segment will start from 10,000 and will go till 15,000. And what if my memory is having only addresses till 12,000, it is not able to accommodate, or there are no addresses which are present inside the memory having 15,000 address. So, in that situation, if you can see a flowchart symbol of a decision box which is around which a yes or no is written. So, only if it is checking the permissible limit. So, only if it is in your D or offset, or we can say limits are in the permissible ranges, then only it is going to generate a final physical memory address and it is being mapped into also. Otherwise, there will be an addressing error, there is going to be a trap which is in the form of the addressing error. Now, after as we have seen this figure, we can say, so CPU we can say, or program is generating, CPU is generating some segments and some logical address spaces are being generated. With the help of the segment table, this logical address is also converted into the physical address, but after checking the limits within the permissible ranges. If yes, then it is going to add the limits. How this addition is going to be performed, I will be taking in an example. And this addition of limits into the base is going to generate an actual physical memory address, actual physical address of the memory. Now, how it is happening, let us take with the help, we will be taking with the help of an example. So, here we have a logical address consisting of two parts, as I told you, and this logical address is generated by CPU. Now, why am I insisting for CPU? Because that is one of the difference between this scheme and the another scheme of paging which we will be covering soon. So, a logical address is being generated which is consisting of two parts. One is the segment number S and another one is the offset into that segment, which is D. Now, the significance of this segment number is it is going to used as an index into the segment table. So, for example, segment number is 4. So, that means that is the entry number in the segment table. So, we will be looking for the entry number 4. So, that is also used as an index to the segment table. Then we have the another part which is the offset D. So, this offset D, offset as you all know, it's a kind of shift. It is going to be in the range of range between 0 to the segment limit. So, it could be either 0, that means no shift, or it could be till segment limit. If it is going to be out of the segment limit, then it is going to give me beyond end of segment address, which is not possible. That means there is an trap to the operating system. That means there is going to be an addressing error. Now, when let us say we have an legal offset as mean starting from 0 within the limits. If we that offset is more commonly known as a legal offset. If it is beyond the limit, it will be known as illegal offset. So, when an offset is legal, it is added to the segment base to produce the address in the physical memory of the desired byte. If it is not legal, then there will be an addressing error, and thus we can say your segment table is essentially an array of base limit register pairs. So, we have some pairs, we have some pairs of registers, and these what registers I am talking about, one is the base register and another one is the limit register, and these base limit registers pairs are segment table is consisting of these base limit register pair. Now, let us try to understand this with the help of an example. Here we have one side we have logical address space and another side we have physical memory, and in between we have a segment table. So, we will be looking at how this logical address space is being mapped into the physical memory. So, logical view of the memory is consisting of 5 segments. So, segment 1 is there, let us say some functions like sqrt or something of that sort. Then we have segment 0 is also there, which is of a subroutine. Then we have segment 3, which is for a stack. Then we have segment 4, which is having some symbol table, and segment 2 is of main program. So, this is what how a programmer perceives about the memory. This stack is in a separate stored in a separate segment. Then we have some symbol table, another in a separate chunk, separate thing, separate segment, and so on and so forth. So as the main program and other functions, library functions and so on and so forth. And then we have a segment table. This segment table is having, we can say, two entries if we say column wise. One is the limit, another one is the base. So the first is the S and another one is the, we can say, shift, which is D. So for example, and the row numbers, if we can say, are the numbers of the segment, and please recall that segments are numbered rather than named. We are going to refer the segments by the numbers, not by the names. So here we have 0, 1, 2, 3, 4. So 5 segments which are being represented, which are being shown in the logical address space. So the first one, which is the segment 0, let's say it is consisting a subroutine. The base of this is 1400 and the limit is 1000. So that means this segment 0 will actually start from base, which is 1400 in the physical memory, and it will go till 2400, the index number 2400, which is essentially 1400 plus 1000. So that is what your segment 0 is. Now let us take a look at the another segment, which is segment number 1, is starting from your 6000 and the limit is 6300, sorry, and the limit is 400. So this will start from 6300, will go till 6700, as you can see in the last of the memory, last of the physical memory. Then we have our, a second number which is also having a limit of 400 starting from 4300. Then we have our third number which is starting from 3200 having 1100 as the limit. Now please remember that for limit we are going to have kind of a permissible number. We cannot say limit is let's say 10,000 or something, because adding 10,000 in any base address, at least in this kind of physical memory, is going to generate an address which will be beyond the limits of the physical memory, which is not allowed here. So that we need to take care, and this is what we were talking about when I was showing the figure, that before the generation of the actual physical address, the limit is being checked for the permissible, or we can say the offset D, which is the shift, is going to be checked for the permissible ranges. If it is in the permissible ranges, then only we can say a physical address is being generated, else there will be an error. So here we have some 5 numbered segment as we have seen, and this segment table has a separate entry for each segment, having the beginning of the address of the segment in the physical memory, which is named as base here, and the length of the segment, which is named as limit here. So for example, we have seen that segment 2 is 400 bytes long, begins at location 4300, and let's say we are referring to a byte 53 of this particular segment 2. So reference to this byte 53 is going to be mapped into the base, which is kind of 4300 plus 53 4353. And what is the permissible range? The permissible range here is actually the 400 thing. Now a reference to the segment 3, which is byte 852, byte 852 of segment 3 is being mapped into 852 plus the base address of segment 3, which is 3200, and that makes a total of 4052, which is also in the we can say permissible range. Now let's say we are going to make a reference to the byte 1222 of the segment 0. Now if you can see in the previous figure, what is the limit of the segment 0? The limit of the segment 0 is only 1000 bytes long. So if there is a limit of the segment 0 which is only 1000 bytes long, we cannot refer to a byte, which is 1222, because this is going to be, kind of, we can say, more than the permissible ranges, and thus it is going to result in a trap to the operating system. Now, in this lecture, what we have covered, we have seen, one of a very primarily used memory management scheme, that is a segmentation. We have seen how this segmentation is going to be performed and what is the, kind of, we can say, hardware component. So, the basic hardware component is, or the basic hardware technique is about the implementation of this segment table, which is having two entries. One is base, which is the starting address of that particular segment in the physical memory, and another one is the limit, that is the reference to the any particular byte or any particular location within that segment will be, kind of less than limit, because let us say, for example, as we have just now seen, that the segment number 0 is having its base, let us say, at 1400 or 400, whatever, and limit is 1000. So, we cannot, address something which is 1300 byte 1300 of base 0, because that is that will go beyond the permissible limits. So, thus we have completed one memory management scheme of segmentation in this lecture, and here is a list of references which is being used for the preparation of lecture. We will be going through other memory management schemes too in the upcoming lectures. Hope you have enjoyed. Thank you.